So, welcome. Today we are going to talk about voltage mode, digital pulse width modulator and sampling method. So, in this lecture we will first talk about trailing edge PWM and digital voltage mode control, sampling delay and control waveform, leading edge PWM and digital voltage mode control, and then digital voltage mode control architectures. So, here we all know about analog voltage mode control, and this you can get detail in our we have also discussed in the week 1, I think it is probably in the 7th or 8th lecture, where we talk about the single loop control. And then if we want to extend this to digital control, then we have also discussed the digitization of the loop. So, here we are assuming that we are already familiar with this architecture, where you need an A to D converter, and this is a discrete time sawtooth waveform, where this is a sampling. A to D converter means we will have a sampler as well as a quantizer and a delay because of the conversion time. So, that means if you want to realize and if you draw the control waveform, then ideally it looks like this. If you take the output voltage sample here, then you need to pass through a compensator, because the output voltage sample value, then it will pass through, and first of all we will subtract from the reference voltage to generate the error voltage. Then the error voltage is passed through the compensator, and the compensator output is nothing but VCN. So, it will also get updated at the same instant. So, we are talking about one sample per cycle, but this is practically not feasible, because we cannot take the sample and immediately process, because there has to be some delay. If we incorporate delay, then as if we need to send the sampling comment here. So, you can see this is my sampling comment, because if you take this our ADC, if this is our A to D converter, and I am talking, this is the voltage waveform, this is a time domain, and this is our discrete domain voltage waveform, and here we are talking about FVS, that is the sampling clock. So, once you send this sampling clock, this is the time, I will say this is the time which will take care about the conversion as well as computational time. But sometimes for hardware architecture, this time is okay, you can take some fraction of switching cycle. But if you go for software based solution, or if you do not want to use too much of resources for high frequency application, then you need to reduce the power consumption. So, for that reason, because we do not want a very fast processing from the A to D converter, then you can use one cycle delay. That means you take the sample here, but after processing the error voltage followed by the compensator, you are actually updating in this cycle. So, that means the controller output is updated in this cycle, whereas the voltage is captured here. So, that means it is a one cycle delay, but it is on a uniform sampling. We are talking about one sample per cycle. Similarly, if we take leading edge modulation, where it is the same concept that we have discussed, though voltage mode leading is not frequently used, but just to understand the leading edge modulation technique, we can again use a decrement counter. If we go for a counter based implementation, then again we can take the sample here, and ideally we can process the control voltage in the same cycle, because this will go through an error followed by a compensator, but practically that is not possible to realize. So, in order to realize, that means the practical conversion, what we need to do, that means if this is your ADC, this is your V0 in time, then this is your V0 in discrete domain, and suppose this is your subtraction, and this is your Vref in digital Vref, and this is our error voltage, then we pass through a compensator. So, this compensator is a digital compensator, and we will discuss how to realize that, and then it will generate our VCN, that is shown here, and then it is compared with the sawtooth waveform. So, by that way we can generate, but there will be delay here, So, to accommodate that, we need to provide a delay, and this is called interval 1 sampling, because we are actually sampling during the on state, when the mode 1. The earlier case in trailing edge modulation, if you go back to the trailing edge modulation, we are talking about interval 2 sampling, because we are actually sampling during the off state of the switch. That is why it is called interval 2 sampling. So, in the interval 1 sampling, here there is no delay, but once you have delay, then you have interval 1 sampling, and this is the time for computation conversion as well as computation. But as I said that you can have a longer delay to accommodate that processing time, because you may not want. Now, you can ask me, for the same ADC, how can we save power by increasing delay? So, if you talk about a pipeline ADC, so a pipeline ADC, actually if you go for a pipeline ADC, suppose this is your time domain waveform and this is your voltage. So, pipeline ADC, the delay, propagation delay depends on the number of clock cycle, how many pipeline stages are there. So, now if we use a fast clock, then the delay can be reduced. If you use a slower clock, the delay can be increased. So, even though the throughput is same, that latency can be high if you use a slower clock for the sampling. But if you want to speed up the conversion rate, then you need to use a faster clock, and that may consume more power. So, you have to be careful about the sampling of the ADC. So, in summary, we have discussed trailing edge pulse width modulator and digital control architecture. Then we have also discussed sampling delay and the control waveform. Then we have also discussed leading edge PWM and digital voltage mode control, and we have also discussed digital voltage mode control architecture, that means leading edge and trailing edge. Though in fixed frequency the trailing edge modulation is often used, but what we have not discussed, how to generate this TRK, that means sawtooth waveform, because we will see there are various type of architecture exist, and we will discuss in the next lecture. So, with this I want to summarize here. That is it for today. Thank you very much.